2.8. I just want to know how you want us to present the answers and the work. It was just finding the distance between 2 points and everything. I guess, for example, I don't know. This is the 2 points: 0 and -6, and then 7 and 1.
Okay, so we want to determine the distance and the midpoint, or just the distance?
Just the distance on this one.
So here's what I recommend. First of all, write the definition. So write x2 minus x1 plus y2 minus y1 squared. So write this. Remember, you cannot simplify it in any way, shape, or form. So the next step I recommend x1, y1, x2, y2. So you don't make an error. Next step, I would write, so I have x2, which is 7. I have x1, which is 0. I have y2, which is 1. And I have y1, which is -6. The reason I'm doing this is because I don't like the nested parentheses. I cannot put minus and minus without parentheses. And then it will mess up the whole thing, and I may not come up with the correct answer. But this is a suggestion. If you have a better method, use it. Forget about mine. So next step, here I see what's happening. So I will write d equals the square root. 7 minus 0. It's 7. And 7 squared will be 49. No number here can be negative. This must be a positive number because it's squared. This is positive. 1 minus 6 will be 1 plus 6, which is 7. And 7 squared will be 49. In order to simplify this, I will definitely write it like this. You're not going to like this, but I will write it as twice times 49. It's 49 plus 49. It's an apple plus an apple is 2 apples. Why I would write it like this? It's because now it's very easy to simplify in case I'm asked to present an exact number. And this is 7. 7 times the square root of 2. Now, if I write 49 plus 49, I get 98. But then I have to say, okay, what do I do with this? I have to simplify it. Okay, it's 2 times 49, and I go back to the same thing. The square root of 2 times the square root of 49. But if I notice that I have an apple plus an apple, which is 2 apples from the very beginning, I don't have to go back and do this. That's not wrong. It's perfect. You have the same thing. But this is what I would recommend. Just look at what you have.
Can you put the paper left a little bit? Half the work is cut off. Just and then put the paper up a little bit. Okay, yeah. So like what you boxed in, that's called the radical, right? What's that called?
The final answer. The distance is final answer.
So the distance isn't the 98 square root, whatever you call it.
Yeah, but you cannot leave it as the square root of 98. You have to simplify it.
Okay, because like, I'm just saying, my math labs and everything was like wanting us to put both answers. So
yeah, in that case, you will take the square root of 98.
Just to put the 7 square root of 2.
So no, you don't need to do that. You just put 98 and you get the same thing. So 9.8994. I don't know how many digits they want. So if they want the approximate.
Oh, they just wanted to round to the nearest tenth. So I put 9.90.
Yes. Oh, yeah. So then this is 9.9. You don't need the 0. It doesn't make any difference, but you don't need it.
Yeah. So I didn't. My answer wasn't the 98. The square root bar around it. I do have distance equals 9.90, but they also wanted the 7 square root of 2 as also an answer.
That's why I wanted to show that the exact. Correct.
Okay, so is there 2 answers to this problem? Is that what you wanted? Or do you
the approximate answer and the exact answer. Correct.
Okay, so you want 2. Okay, that's all I want to know for the test.
Yes.
Thank you.
It depends on what the problem is asking. If it's only asking you the approximate, then you just do the approximate. If it's asking you to do the exact, just the exact. Or if it says both, then both. Good, next problem. Anything else? Other questions?
We don't need to know synthetic division, do we?
No, I did not present synthetic division. I can show it to you if you'd like.
No, thank you. I hate it.
It's much easier than the long division, but the problem is that it's limited. It has limited applicability. So I'm not going to show you an example, but for example, if I have a polynomial divided by x squared plus 3x minus 4, you cannot use synthetic division on this. You can only use synthetic division if the denominator is x minus a number, like, for example, x plus 2, x minus 3, etc. But if it has degree 2 or any other combination here, you cannot use synthetic division. Synthetic division is applicable only in this case. So, but the long division is applicable all the time. So I said, do I show both? Do I show just one? Because we were kind of falling behind. But now we are 2 weeks behind. So, anyway. So I did not show the synthetic division, but if you want, I can.
No, it's fine. Thank you.
Okay, very good. Other questions?
I have a question about
Yes.
how to find the multiplicities.
Yes,
I was struggling with that when I was doing homework.
very good. I'm ready.
I think this is the one that I was doing.
I meant very good that you have a question for us. I didn't mean very good that you're struggling with it.
No, I know. 4x to the third power minus 4x minus x to the fifth power.
So 4x to the third minus 4x minus x to the fifth?
Yes.
Okay. So first of all, I see that this is not arranged in the correct order. So it's negative x to the fifth and plus 4x cubed and minus 4x. Then I realized that the degree is
Negative
the degree.
5.
5.
Good. So how many solutions?
5.
Perfect. So I see that the leading coefficient is indeed negative, and I see that these three terms have a common factor, so I will factor out negative x. In parentheses I have, can anyone tell us what we have in parentheses?
Could you oh, never mind, you're going to move it up. Thank you.
Yeah, I'm so keeping if it's not focused, so maybe I should move this a little bit, because you see here those signs. I have them just to make sure that, is this better? Because these signs are good for that camera where I record. Is this better?
It was better the other way.
Oh no. You
well,
mean
like when you had the camera down when we couldn't see the lines. There you go. It's fine.
Is this better?
Yeah, that's fine.
Okay.
Fine.
So always tell me, because I'm looking at two computers and I just want to make sure that you can see. And I'm recording with the other one that is very clear.
Okay.
And it's right. I mean, the paper is straight, but on this one I could not fix it properly. Okay, ready?
Mm-hmm.
So we factor out negative x. What is left in parentheses? And how many terms? Stacy, is that beeping noise at your end?
No.
Okay. I don't know. I hope it's not at my end. I have no idea. Okay. So what is left in parentheses? Anyone?
X to the fourth plus 4x squared minus 4.
I cannot put plus. If I put plus, negative x times positive, it will not give us positive.
Minus.
Good. That's okay. Minus 4x squared and
Plus 4.
plus 4 indeed.
Wasn't looking at my signs.
That's okay. No worries. Very good. So now remember, you can use a substitution for this, or you can factor it. So if we use a substitution as we did before, let's do that. And then I can show you how to write it in one step. Then I will denote this by t, and I will denote this by t squared, right? And then I have t squared minus 4t plus 4. Can you follow, everyone? Is this okay?
Yes.
Very good. So then this is very easy to factor. Remember, this is what we did on the first day of classes. So this is t minus 2 everything squared. But then I have to go back to t squared, right? Or t. So I know that t is x squared. So this is x squared minus 2 squared. And that's what I'm going to write, x squared minus 2 squared. So this is the complete factored form. And somehow I have to come up with 5 solutions. So I will set this equal to 0. And I have to find 5 solutions.
Can you move it up just a hair?
Better?
Thank you.
Always tell me, because I may not see exactly what you see. I'm not sure. I'm looking at that little window. I don't want to change anything because now it's working. So, okay. So first let's write the equation. I did not write the equation. Negative x squared minus 2 squared equals 0. And then we'll write the solutions. One solution is obvious, which is?
0.
Yes, from here. So these are two identical factors. So I have to write x squared minus 2 equals 0. How do I solve this equation?
Add 2.
Excellent. Which method? Yes, which method? We know 4 methods of solving quadratic equations.
Square root.
Yes, it's specific, clearly done for that. So how many solutions will I get for this equation right here, right now?
2.
Yes. So how do I write them? Which 2?
Plus or minus 2. Square rooted.
Wonderful. I have to show myself. Just for 1 second. I'm back. I'm not hiding. I'm just cold in here. Good. I'm back. I hope it goes back. Okay, good. But we have the second one. So this was one of those 2. So if we repeat, we will get x equals plus or minus the square root of 2 again. So one solution, 2 more, 2 more. So 1 is 0. Multiplicity what?
One.
Thank you. X equals the square root of 2. And x equals negative the square root of 2. How many of this? How many of this?
2.
Remember, 2 plus 2 plus 1 has to equal degree and the number of solutions. So this will be a cross. What will these 2 be when x equals the square root of 2? The square root of 2 comma 0 and negative the square root of 2 comma 0. What will these be?
Turn.
Yes. These 2 are turns. This is a regular cross. Very good questions. Anything
So-
else? Is this okay?
So when you're doing a multiplicity, is it always like, so say that was square root of 6, would the multiplicity be 6?
You mean degree 6? Oh, you mean,
No, I'm
no.
saying like if you wound up getting like, I'm just replacing a number. Like if it was a different number other than 2, would it?
So
does the
if I have the
multiplicity-
square of, so if I have x squared minus 6, let's say to the third power equals 0, I have 3 possibilities for this. So because it's power 3, I have 1, 2, 3. From here, I get 2 solutions plus or minus 6. From here, I get 2 solutions plus or minus 6. From here, I get 2 solutions plus or minus 6. So I get 3 solutions. So I get 3 solutions the square root of 6 and 3 solutions the negative square root of 6. Is that clear?
Yeah, I guess I'm just I don't understand the whole what does the multiplicity thing come in? Like, what do you need that for?
Okay, so multiplicities, if you remember.
Yeah, I also forgot what multiplicity was. I understood it before I went on break, and I completely lost
Okay,
it.
so if I have, when I solve to find the x-intercepts, every time I solve f of x equals 0 to find the x-intercepts, I may get, let's say, x equals 0. I may get x equals 2 twice. Multiplicity 2. Let's say I get x equals negative 3 times.
We can't see what you're writing.
Is this better?
Yes.
So which direction do I have to take this to? Okay, so let's suppose this one appears 3 times. So negative 3 is here. Can you see negative 3?
Yeah.
So multiplicity 3 for x equals negative 3, it means that the function crosses, but very slowly. So it goes kind of flat here. When x equals 0, for example, appears once, then the function crosses straight, right? It does not go slowly. If the multiplicity is 2 and x equals 2, then the function turns. Multiplicities are extremely important for graphing a polynomial function. If I don't know multiplicities, I will not know what happens at each point of intersection, x-intercept.
So
If this solution appears once, it's a normal cross. It appears twice, it has to have a turn. If it appears 3 times, it's not like this. It's very slow.
okay.
So in this case, when x equals positive the square root of 2, we'll have a turn like this because the multiplicity is 2. At negative the square root of 2, somewhere here, will also have a turn like this because it has multiplicity 2. But at 0, it will simply cross like that. This is a very fine-tuned, very specific to polynomials and also rational functions as well. We're going to talk about it now. Very important piece of information. So if you look at the graph, look at the y equals. I'm going to graph 2 functions. So if I graph x squared, I'm going to graph actually, so they don't overlap that much. So I'm going to graph x minus 4 squared. And I'm going to graph x cubed, which we graphed so many different times. Okay, so I'm going to use zoom 6. So here is x minus 4 squared. It has 2 solutions. X minus 4 and x minus 4 equals 0. So it has 2 solutions at 4. This one has 3 solutions at 0. See what happens here? I can zoom in. I can change the viewing window. Let's say between negative 4 and 4 with a scale of 1. See how it crosses? It crosses very slowly at the origin. We graphed that function many times before, see? But if I graph another function, which is, let's say, x plus 4 or x plus 3, oops, I didn't mean the mode, x plus 3, and now I graph all of them, see? X plus 3 has only one solution at -3. And look at this cross, and look at this cross. The multiplicities are so important to know how to graph a function and know what to expect. Multiplicity 3 and multiplicity 1. Multiplicity 2 is a term. So there are even multiplicities and odd multiplicities. The odd multiplicities always cross, but depending on how. The even multiplicity always turns. But again, it depends on how, because you can turn here with multiplicity 2, or you can turn something like this with multiplicity 4. So we need to know that. You have to go back and rework on the problems that we did on polynomials a little bit to refresh our memory on what we did on, and you have all the videos and everything. Is that okay?
What section was this again? To go back
The previous one, 3.2.
Okay.
Good. Other questions for me? Other questions? Okay, so let's start 3.5. And remember 3.5, like the first problem, I always kindly ask you to be patient. It will take me forever because I have so much to tell you about. But then the second problem will take 5 minutes and the next one will take 2. If we don't have any difficulties, right? So the last type of function in this chapter, rational functions. Let me know if you cannot see, okay? So we are going to look at type 1, type 2, and type 3. Are there only 3 types of rational functions? No. But in this class, in algebra, it's all that we can do. Because everything else beyond this, we need a calculator. And that's calculator work, is not understanding much. Okay, so I call these functions type 1, 2, and 3. And I'll tell you why. The book does not call them type 1, 2, and 3. I think if you follow me, you're going to understand this is quite easy to understand, I hope. Okay, type 1. I'm going to give you 2 examples. F of x equals, by the way, a rational function, maybe I should say that from the beginning, is a ratio or a quotient of 2 polynomials. It's a quotient of 2 polynomials. A ratio of 2 polynomials. If there is no x in the denominator, then this is not a rational function. Okay, so a few examples. Let's say x minus 1 over x plus 2. X minus 1 is a polynomial, x plus 2 is a polynomial. Here's another one. F of x is x squared minus 4 over x squared minus 9. Here is of type 2. F of x equals 1 over x. And another example, x over x squared minus 1. Is this color good or not good?
It's bad.
Not good.
Okay, it's out. And here's the last one. These are just examples we're going to choose from here or from the book. It doesn't matter.
Can you push it up a little bit? Thank you.
Sure. Thank you. Okay. So let's see. What do you think this type 1 is telling us? So what do we understand about this? Look at type 1 and say, oh, I think I know. Something specific to both. What is specific to both?
A fraction.
Oh, they have to be all fractions. It's a ratio. By definition, the rational function has to be a ratio. So that's absolutely mandatory. Yes. Anything else that we notice for the first two?
The same degree.
Yes. Same degree over same degree. This one is degree 1 over degree 1. The next one is degree 2 over degree 2. Excellent. That's what it's common. Good, great. So whenever we talk about type 1, then we refer to the same degree over same degree. Excellent. Okay, what about type 2? What do you think? What will you say about type 2?
The denominator has a higher degree.
Excellent, excellent. So degree n, degree greater than n. So here the top has degree, the first one, degree 0 over degree 1. And the next one has degree 1 over degree 2. Great job. Excellent. Finally, the last one, I will not ask you to graph it. I will show you one, but I will ask you to determine something for it, but not graph it. The reason why I think that we should not insist on the third one to graph is because I will not be able to give you too many real life situations. They don't have in the book anything specific, but I'm going to ask you to determine something about this one. Okay, so what do you think about the third one? What would you say?
The degree in the numerator is higher than the denominator?
Exactly by 1 unit. So the denominator has degree n, the numerator has degree n plus 1. Here it doesn't matter. This can be 0 and this can be 5. This can be 1 and this can be 3. It doesn't matter. But here type 3 specifically has to have 1 more in the numerator than the denominator. As you see here, this is degree 2 over degree 1. And this is degree 3 over degree 2. Before we choose a problem from each, I will graph it for you, this one, but I will not ask you to graph it on a test or final exam. Okay, so before we choose from 1 and from 2 and then discuss 3, we have to go through the list of items that we need. I normally shred my paper, so I don't have that in front of me, but we can go back to the lecture notes when we looked at 3.2. Can we go back to 3.2 for a moment? If you'd like to go back to 3.2, when we study 3.2, I'll tell you exactly the date. I'm accessing Canvas right this moment. Okay, 3.2 was accomplished March 11. Actually, March the 9th. Okay, so I will click on March the 9th. On the lecture notes, March the 9th. Okay. So March the 9th, we did not go into these details. So March the 11th, sorry about that. I just got to the handout. I mean to the notes. March the 11th. Okay. You see graphing polynomial functions. Can anyone read the items for us? Graphing rational functions.
You talking about from our notes?
Yes.
Would it be one domain?
Exactly, of course. The same thing, because I would like somebody to read them to see where the differences are between polynomial and rational. What was the next one?
X-intercepts and their multiplicity.
The same thing. X-intercepts and their multiplicities. If they have any. Perfect. Next.
And behavior.
Yes. But then we're going to have to talk about what is called horizontal.
Oh, yeah. Horizontal.
Asymptote. And behavior. Remember, we did not have this concept for polynomial functions. We do now. Good. Next item.
Degree.
There is none for rational functions. Excellent. Great job. Number 4 for us, for here.
Degree.
That's not possible for rational. I have to move on.
Maximum possible of terms.
Not possible for rational. Very good. It can have max min. But there is no maximum possible number of terms. We cannot determine that. Okay, and of course we can use the TI-84 to determine those max min if we need to. Good. Moving on.
Range.
Yes. Range. And
Symmetry.
yes.
Odd or even.
Yep. That's in there. Anything else? And the answer is yes. There is an item. So this is an item that does not exist in polynomial functions. And this will be another item that does not exist for polynomial functions. And this is vertical asymptotes. So this and this are new. Everything else is known. Okay, questions? I think we're not going to get cut off. I think we have the license because they would have warned me by now that because it's more than 40 minutes. Okay. My department came through for us. Okay, perfect. So which problem would you like to start with? We're going to go slowly over each and every item. We're going to use the same table from before to focus all the information, concentrate, and summarize all the information. You want to start with this one? A simple one?
Yeah.
Okay, x minus 1 over x plus 2. So this is our first function. x minus 1, yes, over x plus 2. I change it into x plus 1 over x plus 2 by mistake. Let me change it back.
You can't see what you're writing anyway. Thank you.
Sorry, sorry, sorry. Keep me on track, okay? Because I'm doing this for you, not for me. Very good. I'm going to ask you, what type is it? Is it type 1, type 2, or type 3?
Type 1.
Yes, of course. We haven't discussed any yet. Very good. I have to go through all these steps. The order is not really important, but I have to start with this. That is a must. And I will get my table going from the very beginning. So I'll go back to our list. I'll check them from the list whenever. So I want to add something here. The vertical asymptotes and behavior near vertical asymptotes. Vertical asymptotes and behavior near the vertical asymptotes. We're going to get to that in a minute. Okay, can anyone give us the domain of this function?
Negative infinity to negative 2.
Yes, negative infinity to negative 2.
Uniform.
0 to infinity. Negative 2 to infinity. Excellent. 0 has to be in the table no matter what. Excellent. Great job. Any questions? Is everyone in the clear why?
Just wanting to make sure why we put the negative 2 again.
Okay. Can anyone tell us why?
It's where it's undefined.
Why is this function undefined?
Because of the denominator.
Very good. The denominator cannot be 0. Remember, we started with rational equations in which we have to write that x plus 2 can never be 0. Is this clear, everyone?
So if that was like x plus 3, would you put negative 3 in replacement of negative 2?
That negative 3 will make a 0 in the denominator. That's not allowed. Okay? Yes?
Yeah, I have no idea.
I'm sorry?
Yeah, I have no idea. I'm just gonna watch you do the problem and see if I just understand it better.
X plus 2 can never be 0, so x cannot be negative 2. Is that okay?
Right, so I'm just saying if it was x plus 3, would you put x cannot be negative 3 then?
Yes, x plus 3 in the
That's
denominator
what I
cannot be
was
0. That means x cannot be negative 3.
That's what I was trying to confirm. Because I didn't really get an answer. You're like, I was looking for a yes or no answer, basically, and I didn't understand your answer. But I understood that one. Thank you.
Okay, everyone okay with this so far? Yes?
Yes.
Okay. Well, here's what happens. When a function is undefined like this, a rational function is undefined at negative 2, this line at negative 2 cannot be crossed. So if a function is rational function is undefined at negative 2, this is a line that the function cannot cross. There is no value there. So what can happen is, one option would be that on the left-hand side, the function goes to infinity. And let's say on the right-hand side goes to negative infinity. This situation makes x equals negative 2 a vertical asymptote. The function cannot cross it. The function doesn't exist at negative 2. Is this the only option? No, there are 4 possible options. So if this is negative 2, the function can go to positive infinity on both sides. If this is negative 2, the function possibly can go to the negative infinity on both sides, and reverse these two. So negative on this side and positive on that side. So there are 4 possibilities. So we will determine this very shortly. But for now, I will say the function is undefined at negative 2, and right underneath this, I will write that x equals negative 2 is a vertical asymptote, which means when I end up graphing the function, I will have this line that the function will not cross, and that is a vertical asymptote. So about this, so this is exactly, so what we accomplished so far, we know the domain, and we know that there is a vertical asymptote. Where? Only when the function is undefined. To be exact, after this problem, we're going to look at another problem in which the function will not be defined at a point, but there is no vertical asymptote. So for now, because we didn't get to that specific case, for now we're going to say it's a rational function. It's undefined at negative 2. It will have a vertical asymptote at negative 2. So automatically, I know that left and right, the function will go to infinity. What I don't know yet is the sign of the infinity. How do I determine the sign of the infinity? Very easily. With a number, which I'm not going to put in the table, a number close to negative 2 from the left and close to negative 2 from the right. Like negative 2.1 and negative 1.9. If I replace x by negative 2.1 minus 1, what is the sign of the numerator? Negative, correct?
Yes.
If I replace x by negative 2.1 in the denominator, what will be the sign? Negative 2.1 plus 2.
Negative.
Good. So I had negative over negative. So what is the sign of this infinity for sure?
Negative. I mean positive.
Very good. I know exactly it's going to positive infinity, no doubt. Okay, let's plug in negative 1.9. Negative 1.9 minus 1. What will that sign be? Negative 1.9 minus 1. I have 2 negative numbers, so it has to be negative, right? But the denominator, negative 1.9, but now plus 2. What will that sign be?
Positive.
Yes. So I have a negative over a positive. What will be the sign of this infinity to the left, to the right of negative 2?
Negative.
Negative.
That's it. And this is done. Item 7 is done. Okay, so now let's talk about the x-intercepts. And of course, we have to add here the x and y-intercept, right? So we need one more item. We have to add one more item. I jumped.
So the vertical asymptote is negative 2 then?
The vertical asymptote is x equals negative 2, is this line, not negative 2. It's x equals negative 2, the vertical line.
And then the end behavior is
No,
example.
we haven't gotten to the end behavior yet. We're only talking about number 7, vertical asymptotes and behavior near the vertical asymptote.
Oh, okay, sorry.
That's
Sorry,
okay, that's okay. Which is positive infinity on the left and negative infinity on the right.
Okay, sorry, I read it wrong.
No, that's fine. Good, so let's determine the x and y intercepts now. So I remind you the function is x minus 1 over x plus 2. How do I determine the x-intercept?
The function equals to 0.
Say it again, Bernie.
The function equals to 0.
Excellent. So x minus 1 over x plus 2 equals 0. When is a fraction 0?
The denominator?
Never. The denominator cannot be 0.
Oh, no, the numerator.
Exactly. Very good. Which means x equals 1. Great job. A fraction is 0 if the numerator is 0, which means x equals 1. Great job. I put in the table 1, 0. Now I want the y-intercept. How do I determine the y-intercept for this function?
Add 0 in for x.
Excellent. Thank you very much. So 0, 0, so I have negative 1 over 2. Negative 1 over 2. Negative 1 over 2 in the table where it belongs. 0 for x, negative 1/2. 1 for x, 0 for y. Since x equals 1 appears once, is this a turn, a cross, a slow turn, a slow cross? What is it? It has multiplicity 1. What do we? Cross, a regular cross. Very good. Excellent. One more item. We're interested now in the end behavior. And as you see, the end behavior, so we finished this. We're going to talk about this in a minute. Horizontal asymptote and end behavior. Okay, so let's talk about that. So the function is x minus 1 over x plus 2. Forget about the numerator, the denominator. Just tell me the degree of the numerator.
1.
Yes, so I'm going to factor out x. And you could say, wait a minute, you can factor out x, as is not a common factor. I agree, it's not. I'm not going to ask you to do this. I just want to explain the end behavior. You don't have to do this. Just follow my explanation. So would you agree that this is 1 minus 1 over x? X times 1 is this. X over 1 times 1 over x is 1. Do we agree with that?
Yes.
Yes.
Good. The degree in the denominator is still 1. I'm going to do the same thing. I'm sorry, I meant 1. 2 over x. I will simplify x with x. And remember, when we talk about end behavior, we know that x is huge. Negative or positive, but huge. So if I divide a cake by 2 people, we have each half. If I divide it by 3 people, each gets 1/3. But if I divide it by something huge, infinite, because that's what we are talking about, we want to determine the end behavior. So if I divide a cake by 10,000 people, how much will each get? Almost what? If I divide one cake by 10,000 people, how much will you get?
Very small.
Very small. This quantity approaches 0. This quantity approaches 0. So this is 1. I shouldn't put the equal symbol. This is not the equal symbol. This approaches 1 because it's the leading coefficient over the leading coefficient. So this is 1 and this is 1, which means y equals 1 is a horizontal asymptote. What does this mean? It means this, that this function will either do this, or maybe this, or from here, but it's not a function. I cannot draw this once I draw that. So it means that as x increases tremendously to the negative side and the positive side, the function values will get closer and closer to 1. The function values will get closer and closer to 1. And that's the end behavior. So the end behavior for this function is y equals 1 is the horizontal asymptote, and the end behavior is 1. So this function is not symmetric. It cannot be symmetric if it has a vertical asymptote at -2. So, but I have to write that. F of negative x does not equal f of x. We wrote this like 15 million times already. I'm sorry?
Move the paper up.
We wrote this, yeah, we wrote this many times before. So not symmetric. Okay, now I would like us to slowly and surely, this is the end of it. We want to graph this function. It's a rational function. So when we graph a function like this, let's go back only to, that's all I care about, all the information is here. I will start with the vertical asymptote. It's not part of the graph, but I have to graph it. It's not a solid line. I will write x equals -2 VA. I will continue with y equals 1, the horizontal asymptote. And now the function. This side says, from approaching 1, go to infinity. From approaching 1, go to infinity. Approaching 1, go to infinity. On the left-hand side of the vertical asymptote. From 1, don't touch. From 1, although I'm going to write down that a function can cross the horizontal asymptote, but it will never cross a vertical. So from 1, go to infinity. Okay, let's see here. 0, -1/2 is this point. 1, 0 is this point. Let's see what this is telling me. From -infinity, cross the y-axis, cross the x-axis, and go closer and closer to 1. That's all this says. From -infinity, cross the y-axis, cross the x-axis, and approach 1. This is the graph of the function x minus 1 over x plus 2. Let's grab our calculators and verify all this with the graphing calculator now. So in y equals, clear everything. I had 3 functions in here. I'm clearing all. And I will put in parentheses, please be very careful, parentheses for the numerator as x minus 1 and divide by, in parentheses, x plus 2. The graphing calculator is not as smart as you are. It does not know that the function has a horizontal asymptote at 1. So this is a totally new function, y equals 1. Let's use zoom 6. Here comes the function. Here comes the horizontal asymptote. As expected, from approaching 1 going to infinity. The graphing calculator does not present the vertical asymptote, or I don't know how to present it. Maybe there is a way. The old calculators that I have, they come with a vertical asymptote. So I'm not sure with this new one how to make it. If you discover that, please teach me how to graph the vertical asymptote.